Okay, so today we are looking at two different big topics. Well, actually three. The first is determining percent composition. Then we're going to do limiting, not limiting, that's tomorrow. Back up. We're going to do empirical formulas and molecular formulas, and then stoichiometry. Three things that we took like quite a few days to cover in pre-AP and in Chem 1. So first we're going to determine the percent composition of each element in nickel 2 phosphate. Percent composition is based on the molar mass of the periodic table. Okay? It's not based on literal grams I have. When I want to know percent composition, I want to know how much nickel is in, what percentage of nickel is going to be in any sample of nickel 2 phosphate. How much phosphorus will be in any sample based on the set subscripts in that compound. Okay? So what I'm going to do first is figure out my total molar mass of the substance from the periodic table. So let's do that. 3 nickels times how many, plus how many phosphates? Phosphoruses, I should say. 2 phosphoruses and how many oxygens? 8 oxygens. So does anyone have that total? Quickly. Sorry, those at home. My class is a little bit slacking today. You're laughing, but you're not adding anything up, Mr. Wang. Okay, this is not really good. 366.01. All right, so that's how many grams per mole always exists in ratio. So if I want to find the percent of each element, I'm going to look at each element and how much of that is in that, how much of that makes up that 366 every time we have nickel 2 phosphate. So if I look at the percent of nickel, I'm going to take my total mass of just nickel divided by the absolute total mass times 100. So if I have 3 nickels, what's the mass of those? 3 nickels. Point what? 10. Okay, we want 2 decimal places, folks. All right, over the whole of 366.01 times 100. So what's my percent of nickel? We'll stick with 3 sig figs here. I'm not going to be super crazy about sig figs when it comes to this kind of thing because we're arbitrarily deciding what to round this to. So there's no measurement in this, so there's really no true worry about that. So are you telling me it's 40? You're telling me it's 0.485%, or are you telling me it's 48.5%? 48.1? Okay, good. Let's try phosphorus. So if I do my phosphorus percent, I've got 2 phosphoruses. What's 2 times 1 phosphorus? Divided by my whole of 366.01, and we get 16.9%. All right, and then the last one is oxygen. How many total oxygen? 8. So what's 8 times 16? Is it point? All right, and what's our percent of this? 35.0? If we do our stuff right, we should get a total percent of what? 100. And if you're off a little bit, it's a rounding issue. Don't freak out about it. It'll be okay. Normally, they won't ask you questions about they won't ask you all the percents normally. They'll just say, what's the percent of carbon in carbon dioxide? And that's it. So you'll just have to do it based usually for just one element. Okay? All right. Let's move on to our next slide that I can't see where the page turner is. There it is. Okay. Empirical and molecular formulas. What's going on, boys? 100.8. Is math tough for you? Yeah. Okay. So empirical formula versus molecular formula. Who remembers the difference? Grant? You simplify empiricals, or how about, okay, I see where you're going. He's saying you get them down to the most basic term possible. I know what you're saying, but you don't get them down to that. An empirical formula is, by definition, the lowest whole number ratio. It itself is already simplified to the lowest whole number ratio, okay? So an empirical formula is the lowest whole number ratio. And then he was correct when he said molecular formula. That's pretty much how you find it in nature. An example of this, which I don't know if you've thought about, is this. And this doesn't relate to this problem at all. What's that? Sugar. We're in chemistry now. That's not sugar. What is that? Glucose. Correct. Glucose is a molecular formula. Why isn't this the empirical formula? It's not the lowest whole number ratio. If I were to get the empirical formula for this, what would it be? CH2O. As a matter of fact, your trivia piece of knowledge for the day, this is the empirical formula for all carbohydrates. Carbohydrates. It's kind of cool. So your carbohydrates are all going to be multiples of this empirical formula. All right, so sometimes your empirical formula can be the same as the molecular formula. Larson, feet in front of you. Stop turning around. Sometimes they're the same. Like water is molecular and empirical because it itself is at the lowest whole number ratio already. So now let's take a look at how to do this problem. My rule of thumb normally is to write these compounds in the order you find them in the problem. You don't know any better, write them in the order. I happen to know that this is out of order, so I'm going to put them in the order of C, H, and Cl. Okay. Again, from here on out, I want you to put them in the order they give you. Notice they give us percents. The first part of any problem is to you need grams of each element in order to do these problems. Since we don't have grams, we have percents, there's an assumption we have to make. Does anyone remember that assumption? We assume a total of how many grams of compound? 100 grams total. If we know we have 100 grams total of this compound, we now know how many grams we have of each of these. So we end up having 24.27 grams of carbon, 4.07 grams of hydrogen, and 71.65 grams of chlorine. Now, we really can't compare grams because they all have different molar masses. So the next step will be converting to moles. So now we have to convert to moles. So how do we convert each of these to moles? Find the molar mass of each and divide. So for every 1 mole of this, I have 12.01 grams of carbon. For every 1 mole of hydrogen, I have 1.01 grams. And for every 1 mole, 35.45. Yes? 45 grams. All right, so next we're going to find moles. The best thing for you to do is to carry out these sig figs, carry out a lot of sig figs, because it's going to help us when we're trying to figure out if we have a half a mole or something that we have to multiply by later. So don't be shy with the sig figs here. Divide all of these to get me moles. Carbon. Louder and more numbers, please. Thank you. Wake up, guys. This is torture for me right now. Come on. I need a little energy. Hydrogen. How many moles? And then chlorine. One. All right, so those are all my moles. If I want the lowest number mole ratio, I can't just take C2H4Cl2 because that's not going to find me the lowest whole number ratio. So what would be the thing to do? Exactly. Divide by the smallest. All right, so my smallest looks to be 2.018. All right, 2.018 is my smallest, so that gives me a 1 here. What does this give me? I want you to put it in the calculator. 1.996, and then this is 1. All right, so you can round to the nearest whole number if they're this close, okay? But if it's like a 0.25 or a 0.5 or a 0.3 or a 0.75, that's not close enough to round, and we'll have to do something different. But for all intents and purposes, this is a 2, and this is a 1. Okay, so now that we know that, we can figure out the empirical formula. What is our empirical formula? CH2Cl, right? Okay, our empirical formula looks good. In the problem, I can't see it. What did they say the molar mass of the formula was? 98.96 grams per mole. Now, this molar mass is not the mass of the empirical formula. It is the mass of the molecular formula. So we need to find the molecular formula. We have found the empirical formula, so I'm going to write EF here. If I know that this is going to be a multiple that's evenly divided into the molar mass of the empirical formula, of the molecular formula, what would I need to do? Because I need to find the molecular formula here. That's my job. Any ideas? Perfect. Find the empirical formula mass first. So add those up and tell me what you get. You can kind of round this here because I'm going to tell you something. 49.48-ish. All right? The reason I'm saying ish is this is an internal check. If you take your empirical formula mass and divide it into the molecular formula mass and you don't get really close to a whole number, you have messed up. Okay? There's really no excuse for missing an empirical formula if they give you the molecular formula because you have an internal check. All right? So looking at this, does 49.48 divide into, so we're going to take the molecular formula mass divided by the empirical formula mass, and we're going to get a number. What do we get? 2. That looks great. Since I know it's 2 now, I can figure out my molecular formula, and what is that? C2H4, and that is my molecular formula. Okay? Sometimes you divide them, you're going to get a 1. What does that mean? Empirical formula is the same as the molecular formula. Got it? All right. Let's do another one. Determine the empirical formula for a compound, and now we're going to stay in order. I want you to put things in order that you get them. They're percents, so we're going to assume 100 grams and write these as grams. We've got potassium at 26.6 grams. We have got chromium at 35.4 grams. And then we have got oxygen. I can't see it. I don't know where it went. Can y'all see it? 38.1 grams. First thing we're going to do is determine the empirical formula. And then it also tells us that our molecular formula has a mass of 294.2 grams per mole. We'll look at that later. But right now we need the empirical formula. So my first step, loud and proud, is to do what? Convert to moles. So I'm going to divide all of these by the molar masses. For every 1 mole of potassium, I have 39.10 grams. How many moles is that? Give me more sig figs than that. Yeah, you don't have to go that far. I like how y'all are so black or white. You either give me 3 or you give me 18. Chromium. Molar mass? Again? 51.99 or 51.2? 52.0? Y'all aren't. I cannot hear what y'all guys are saying. What? Wow. 0.6803. All right. What's this? Moles? Okay. And then my moles of oxygen. .3813. Okay, so there are all my moles. What do I do now? Divide by the smallest. What's my smallest? Potassium. All right, so I get a 1 here. I get a 1 here. What do I get here? A 3.5. That is way too far from a whole numbered around. Okay, so I can't have KCrO 3.5. Totally not going to happen. So what do you think I need to do? Double it. Is it still a smallest possible whole number ratio? Absolutely. That's not any further divisible or can be reduced anyway. So this is my empirical formula. My molecular formula is over there. What's my first step? Find the mass of my empirical formula. Empirical formula mass is equal to, add them up. I have a feeling. I think it's 294. And it is. So that comes out to 294. So what is K2Cr2O7? It's potassium dichromate, and this is also the molecular formula. The fact that you could name it like that was a good indication that it was the molecular formula as well as the empirical formula. Potassium dichromate. Okay? Any questions on this? You're just going to have to practice more of these because we're moving on to stoichiometry now. Stoichiometry is one of my favorite things in the whole world. Okay. First thing we're going to do, though, in preparation of doing stoichiometry is doing something called balancing equations, which I'm really not going to go over too closely with you. I'll practice one with you. So we're going to balance this equation, and then we're going to draw a particulate diagram showing the balancing. Okay? So when you have an equation like this, who remembers what type of equation this is? Look at it. It's a combustion equation. My suggestion, because these can get kind of hairy, is to save your oxygens for last in balancing, since those oxygens show up in 2 of the products. Because if you try to do those first, you get confused. So I would start with your carbons and hydrogens. So what do you want to start with? Carbon. We have 2 there, so we need 2 there. Hydrogens, how many on this side, the left? 6. So how many do we need here? How many waters? 3. How many oxygens does that give us on the right side? 7. I've got an O here and 2 here. What do I need to do? Put a 3 here. And that means it's balanced. So to draw this particulate diagram, I don't want you to freak out. These drawings I'm talking about right now don't have bonds in them. You don't have to worry about numbers of electrons. We're just drawing little balls as atoms, okay? So I'm going to go ahead and make carbon black, because carbon usually in model kits is black. And then I'm going to make my hydrogen red, Usually it's white, but drawing white's kind of tough on the board. No. I'm going to make oxygen red, because in kits, oxygen's red, carbon's black. What color do you want to make hydrogen? Green. Hydrogen's going to be green. Now, I know from experience the way that alcohol is built. I've got my 2 carbons attached, and then I got my hydrogens around, and my OH is together as a group on one of the carbons. So I'm literally, don't freak out about these. Carbon, carbon, right? And then I'm going to have an OH hanging off of it because it's an alcohol. And then what do I do with the rest of the H's? Put them on the carbons, right? So I'm gonna have 5 to pass out. So I'm gonna put 3 here and then 2 there. And then each carbon has basically 4 bonds if you think about it. Carbon to carbon's a bond, and then it has 4 bonds. Okay, so there's my ethanol. How many ethanols do I need in this particular diagram? Just the 1. Okay, so how do I draw 3 O2s? Do I put all 6 oxygens together? No. What is this called? A diatomic. So I'm going to put those 2, 1, 2, and 3. Yay, these are so pretty. So on your tests, if you don't have, you're not going to have colors. Probably won't give you more than 2 or 3 things to draw. You can do empty balls, solid balls, patterns. There's different ways to do it without actual color. All right, CO2s. I've got 2 of those. What do those look like? Carbon. How are the oxygens? Are the oxygens attached to each other? No, they're attached to the carbon, right? Since I have 2 carbon dioxides, I'm going to need 2 of these. And then each of those are going to have 2 oxygens on it. I should draw them linear. You don't have to, but I know it's a linear molecule. And then waters. How many waters? 3, right? So I'm going to put my O's in the middle, and then 2 hydrogens on both. I happen to know water's bent, and you will at some point. At this point, I'm not holding you responsible for that, but I think you can handle drawing it bent. Once we get to shapes, I will expect you to draw it bent. I'm going to redraw this because it's not linear enough looking. Now, the way you can see is based on what we drew. Do we have the same number of all the colors on both sides of this? Yay, nay? Yeah, we do. Okay, so that's a particulate diagram. All right, let's do some stoichiometry now. The drawings were fun, but now we get back to real chemistry. Determine, can I go this way, I wonder? I don't know if I can move to the left. Maybe I can do this. What I drew was enough. Okay. Determine the amount of iodine produced when 145 grams of Ki react with excess copper 2 chloride. So what I want you to be able to do here is, I call it secretarial work. I'm a big fan of recording all your things in a manner that you never have to go back up and read that question again. Because that's where students mess up. They forget what they're looking for in the problem. They get all confused. So step 1, do I have a balanced equation? And yes, it looks balanced. The next thing I do is take the information and translate it to the equation. I'm looking for the amount of iodine produced. So I'm looking for grams of that iodine. When 145 grams of Ki react with excess copper 2 chloride. When I see excess like that, I put an X through it because I know that's going to be extra. I'm going to run out of that. I'm never going to do stoichiometry from there. Now, what is this stoichiometry I keep saying? Stoichiometry is the mathematical relationship that exists between all these compounds. For every 2 of these, I have 4 of these, 2 of these, 4 of these, and 1 of those. So I can do stoichiometry anywhere in the equation. Knowing this, I can figure out how much this I use. Knowing this one, I can figure out how much that I use. I can go from product to product. I can jump all over the place. That looks like a happy face. That's so cute. I can jump all over the place and do stoich like that. So just know it's not only a reactant to product thing. So with that being said, I'm going to do stoichiometry from here to here. That arrow, I call it the mole bridge. To get across the mole bridge, what do you think you have to be in to get across the mole bridge? Moles. Yes, Christopher?
Do you have to do anything extra with the iodine on the copper?
Why are you asking? Why do I need to do something extra? What's making you think that?
We're trying to find the amount of iodine produced.
Right. Are they asking for the amount of iodine in compounds? No, they're asking for iodine that's as its own compound. So I see what he's saying. He's wanting to include this iodine as well because that's iodine, but that's not I2 production. Okay, that's I in another compound. So we are going to just stoich from here to there. I'm going to start with my given, 145 grams of Ki. Now I want to cross the mole bridge, so I have to be in moles. So for every 1 mole of Ki, how many grams? 156 or 66? 66.06 grams of Ki. I'm going to be a little more insistent that you write grams and moles of what in these because we're going to have 2 compounds included in our dimensional analysis. All right. Now I'm going to cross the bridge. At the beginning and the end of the bridge, I've got gatekeepers. These gatekeepers will not let you on or off unless you know the password. The password is the stoichiometric ratio to get on and off. So, for every 4 what? Moles of Ki, that's my mole ratio. I have 1 mole of I2. So now I'm just going to go back, my grams canceled, my moles of Ki canceled. Now I can get off the bridge and I'm in moles of I2. How do I get to grams, which is what I'm looking for because it asked for amount. I know amount technically could be moles, but that's not a very useful number for us. Okay? How many grams per mole of I2? What was that second number? All right. Again, all I'm looking for, arbitrarily, we've decided as a class to round our molar masses to 2 decimal places. We will never utilize any of those for sig fig determination because they're not measurements. All that matters is at the end of the day, I round the final answer to 3 sig figs. Now let's say you did leave at 354 and we left at 253.8. Your answer might be a little different than ours. But on the AP, as we read, we are aware of that. You won't lose points as long as that final answer is rounded to the appropriate sig figs. So what is this number? Grams of I2 is produced. Got it? Got it. All right, let's go on to the next one. I like this one. This is a consumer problem. This is going to help us figure out what we should take when we have an upset stomach. Baking soda. Back in the day when I was a kid, my mom used to take baking soda, stir it in water, and make me drink it when I had, like, acid reflux or whatever. I mean, it's technically the same thing as what we take now with milk of magnesia, which is magnesium hydroxide. So they're giving us the reactions of both of those things with hydrochloric acid, and that's what's in our stomach. So their question is, which is more effective? Which is the more effective antacid per gram? Sodium bicarbonate, which is the baking soda, or magnesium hydroxide, which is the milk of magnesia that most of you buy today. So, any ideas of how to approach this? Per gram is 1 gram. So they're comparing a gram of this and a gram of that. What are we trying to figure out when we say it's more effective? We have acid reflux. The more effective one is going to do what? Okay. What's the goal of taking the antacid? To reduce pain by doing what? Reduce acid by neutralizing the acid, right? So, a way we could measure it is to see how many grams of acid are neutralized with that 1 gram of base. So I could do stoichiometry And I could go, okay, if I have 1 gram of this, if I do stoichiometry from here to here, doesn't that tell me how much acid reacted with that gram? Yes or no? Yes. And if I do 1 gram of this and do stoichiometry from here to here, doesn't that tell me how much acid reacted with that 1 gram? So which one would be the best, more effective one? Right, the one that reacted with more of the acid. So we're just going to do 2 stoichiometry problems really quick. The first 3 rows, I want you all to have sodium bicarbonate mass ready to go. These last 2 rows, I want you to have the molar mass of magnesium hydroxide ready to go. Okay? So to set this up, I'll do sodium bicarb in red. So I'm going to start with the 1 gram. I take 1 gram in to my body. And I should write the units, bad teacher. Sodium bicarbonate. There's our baking soda. And for every, I want to cross the mole bridge, so I've got to get into moles. So for every 1 mole of sodium bicarbonate, I have how many grams? Oops. Yeah, that's right. First 3 rows, that was your job. Molar mass. Thank you, Irene. All right, 84.01 grams. Now I need to cross the mole bridge. What do I need to do to get to the moles of HCl? Nice. For every 1 mole of baking soda, I have 1 mole. Good job, Alex. All right, got that done. Now how do I get to grams? For every 1 mole of HCl, I have about 36 grams. 36 point what? 46 grams of HCl. So how many grams of HCl did 1 gram of sodium bicarb neutralize? So let's stick with whatever, this is fine, 2.30 grams. I'll stick with 3 sig figs. There really is no measurement here. We don't know per gram how significant our 1 is. Is that wrong, Larson? 0.03? 0.4339? So 0.434. How'd you do that, Larson? Oh, okay. Got it. Because you did it in your head and didn't write it down? Is that why? Oh, you did? Okay. Grams of HCl neutralized. All right, now let's do the same thing for the milk of magnesia. So for every 1 gram of OH2, got to get to moles. Group 2, what is my molar mass? That's the way to represent. Whatever. None of you even picked up your calculators. All right. Now how do I cross the bridge? For every 1 mole of MgOH2, I have got, nice, 2 moles of HCl. Okay, and then for every 1 mole, I still have 36.46 grams. So how much does this neutralize per gram of base? Louder?
I got 2.57. I got 1.25.
Okay, 1.25. Wow. So which one are you going to take? Milk of magnesia. Thanks for nothing, Mom. Thanks for making me drink that nasty stuff instead of going to the store and buying me some milk of magnesia. All right, last problem. Are y'all good with this? I'm weirded out by the difference in our number there. Is that, I guess it makes sense because we don't have the 2 and that's yeah, it's probably fine. I don't know. Is this right, this top one? Are we 100% sure? Okay, thanks. All right, last problem. Dun, 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 dun. Don't let this problem scare you. What this problem basically is a series of chemical reactions that are used to pull out zinc from zinc sulfide in ore. Okay? So the problem is wanting to know, given a particular piece of ore, so here's my piece of ore. Okay? Piece of ore is going to have some zinc sulfide in it. Now, it's more homogeneous than this. It's not going to be all splotchy like a disease. But this problem is giving you a piece of ore, and it's saying this whole piece of ore weighs 10 kilograms, which is 10,000 grams. Okay? The question is asking, how much of this zinc sulfide is in this 10,000 gram piece? What percentage of this is zinc sulfide if, after this thing was put through the chemical process, we produced 2.85 kilograms, which is 2,850 grams of zinc? Don't let it scare you because it's still just stoichiometry. Do you see how zinc sulfide is here? Anytime you have a chemical process like this that happens in multiple reaction, there has to be a link. So what would be a good thing? We're going to have to go backwards now. We're going to have to do stoichiometry that way, from product somehow getting back up to zinc sulfide. So what would be the link? What should we do stoic to? To zinc oxide, and then we know zinc oxide, then we can do stoic directly to zinc sulfide. We can stoic on over. So I'm going to start with I'm starting backwards. I'm going to start with my zinc, and I'm going to say there are 2,850 grams of zinc, right? Okay. I want to cross that mole bridge. I believe those equations are balanced. We should always check that. I should have brought that up to you. But yeah, we want to make sure that's balanced. How do I cross the mole bridge? Moles. For every 1 mole of zinc, how many grams do I have? 40 grams. 41 grams. All right. Now we're in moles of zinc. Now what do I do? For every 1 mole of zinc, what does zinc oxide remind you of? Sunscreen. I remember that stuff that you put on, the colored stuff. One of them was called zinc something or other. Zinca. Why is it called that? Zinc oxide. All right, 1 mole of zinc oxide. Now, how do I make the connection? Good. For every 2 moles of zinc oxide, I have 2 moles of zinc sulfide. So that's my second stoichiometry. And then how do I get to grams of zinc sulfide? For every 1 mole of zinc sulfide, I have, quick, 97 point what? 44, thank you. 97.44 grams. So tell me my grams of zinc sulfide that had to be there to make that much zinc. Meaning, do the math. That sounds a little bit better. Say it again, Alex.
4,245.59.
So let's just say, give me 3 sig figs. 4,250. 4,250 grams of zinc. Is that the answer to the question? No. What is the question asking? It's not zinc. Sorry, it's zinc sulfide. The percentage of zinc sulfide in my original ore. Remember, my original ore weighed 10,000 grams. So I'm going to divide part over a whole times 100. So I believe that gives me 42.5%. They just high-fived back there again. Zinc sulfide in the ore. That's a pretty sexy problem. You'll hear me say problems are sexy, and that's a sexy one. Okay? Any questions? All right, you have about 4 minutes. You can be working on your homework. And then tomorrow, I'll get off the video to talk about tomorrow.